The proposed benchmark for evaluating human automation interaction, HI, systems integrates human factors, cognitive engineering, and artificial intelligence to assess both front-end and back-end components. This approach aims to provide a holistic evaluation, capturing the complexities of human-centered metrics and technical performance. The benchmark is based on cognitive engineering models that describe human reasoning, particularly judgment and prediction, which are influenced by environmental cues and strategic goals. The lens model is also reviewed, detailing how individuals discern and decide in ambiguous settings, and how cognitive biases and heuristics affect judgment and prediction. Evaluating these factors' influence on human interactions with automated systems is crucial in HI, as they can lead to predictable errors in decision-making. The benchmark would fit systems that support human decision-making, such as the one developed in Rovira et al., where users interact with an advisory system at different levels of automation. It assesses the alignment of the HI system to cognitive efficiency and its inverse, ensuring efficient collaboration and minimizing errors in high-stakes stochastic environments. This novel approach addresses the limitation of existing benchmarks, which often failed to capture the full spectrum of human-centered metrics, focusing instead on technical performance alone. By providing a structured approach to quantifying the efficacy and reliability of HI systems, this benchmark facilitates a more comprehensive evaluation, driving innovation and progress in the field. In the context of human automation interaction, the recognition primed decision model and cognitive continuum theory are essential for understanding complex decision-making processes. The increasing trend of automation necessitates the development of a benchmark to quantify the complexity of human automation systems, particularly in hybrid ecologies. This benchmark should measure automation failure, which can be defined as software glitches, hardware breakdowns, or unintended applications of automation. The lumberjack model illustrates the abrupt decline in task performance when automation encounters failures beyond a certain degree of automation threshold. A preliminary taxonomy of automation impairment mechanisms is introduced, comprising 4 categories: elementary automation failures, systemic automation failures, human automation interaction breakdowns, and human and organizational slips and misconceptions. This taxonomy can identify gaps in human automation system interface design and training. Simulation environments with tests or tasks must be created to apply a benchmark to an HAI system, such as the sensor-to-shooter loop simulation, which evaluates operators based on decision-making accuracy, response time, secondary task performance, and subjective ratings of mental workload, trust, and self-confidence. The research explores the impact of imperfect automation on human performance, highlighting the first automation failure effect, and the importance of designing automation systems that are not only accurate but also consistently reliable. The study concludes that automation significantly impacts operator performance, particularly influencing response times and accuracy of decisions in command and control tasks. The authors propose benchmarking as a methodology to iteratively perfect a system in a testable manner, emphasizing the need for continuous benchmarking development to evaluate AI models in human automation interaction systems and assess the explainability of system behavior in high-stakes contexts. This research paper emphasizes the need for developing quality metrics to evaluate the performance of artificial intelligence (AI) models, particularly large language models (LLMs), and human AI interaction (HI) systems. It highlights the importance of benchmarks in AI, such as accuracy, precision, recall, and F1 score for tasks like image recognition and language processing. For LLMs, benchmarks like Squad and Glue evaluate language comprehension and generation. The authors propose a benchmark design for HI systems, focusing on decision-making accuracy, response time, secondary task performance, and subjective ratings of workload, trust, and self-confidence. Novel metrics for HI systems include component interaction balance, overload penalty, attention span efficiency, and cognitive strain index, which aim to quantify different aspects of human automation interaction. These metrics are grounded in various theories like Brunswick's lens model, cognitive load theory, and Miller's magical number 7 theory. The development of these metrics is crucial for evaluating HI systems efficiently and ensuring decision-making processes are optimized. Human automation interaction (HI) systems are evaluated using various metrics, focusing on optimizing cognitive resource usage, reducing information overload, and ensuring system responsiveness. The wasted attention resource (WAR) metric targets underutilization of cognitive capacity, while the noise index (NI) quantifies excess cognitive load. The interaction redundancy (IR) metric evaluates unnecessary duplication in back-end processes, and operational latency (OL) measures the delay between user action and system response. The critical risk index (CRI) assesses risk due to overlooked system interactions, identifying high-risk scenarios. These metrics aim to create a benchmark for the field of high, human factors, and cognitive engineering, considering cognitive load, system efficiency, and risk management. Future work involves testing and evaluating these metrics in different tasks and making them compatible with various high systems. Machine learning, ML, and statistical models can optimize human automation interactions, mitigating automation overload effects. Evaluating the balance and efficiency of these interactions is crucial, and ML models can serve as metrics, predicting when back-end complexities may overwhelm the user and optimizing system feedback timing and clarity. The paper provides an extensive index of cognitive engineering models, translating them into evaluation metrics, such as policy capturing, signal detection theory, and naturalistic decision-making. Key concepts include cognitive alignment, taxonomy of automation impairment mechanisms, and performance metrics like component interaction balance, overload penalty, and feedback efficiency. The framework modules focus on human performance and system performance, with an example application on the SDT eval demonstrating real-world scenario applicability. The paper highlights the role of ML and statistical models in enhancing human automation interactions, reducing automation overload risk, and developing more efficient and balanced systems. The research paper discusses various evaluation metrics for assessing human decision-making in different domains. Policy capturing models the pilot's judgment process as a linear additive model, deriving weights through regression analysis. Signal detection theory evaluates accuracy in detecting signals amidst noise, while naturalistic decision-making measures decision-making efficiency in real-world contexts. The coherence model eval assesses the coherence of judgments made by operators in automated systems. In robotic surgery, the cognitive continuum theory evaluates the balance between intuitive and analytical decision-making. Brunswick's lens model assesses cue interpretation accuracy in spacecraft monitoring, and cognitive alignment in aircraft piloting evaluates response to cockpit alarms. These evaluations demonstrate the application of cognitive theories in various domains to understand decision-making processes and their implications. The research discusses various metrics to evaluate the performance of human automated interaction systems, focusing on aircraft piloting. It begins by defining elementary automation failures, EAF, and systemic automation failures, SAF, quantifying them with weighted elementary automation failure, WEAF, and weighted systemic automation failure, WSAF, scores. Additionally, human automation interaction breakdowns, HAIB, are measured using the weighted human automation interaction breakdown, WHAIB, score. The component interaction balance, CIB, is also introduced to assess the interaction balance between user input and system response. The evaluation of these metrics aims to optimize system design and minimize cognitive overload. Further, the research presents several metrics for evaluating human automated interaction in aircraft piloting, including overload penalty, OP, attention span efficiency, ASE, wasted attention resource, WAR, noise index, NI, interaction redundancy, IR, and cognitive strain index, CSI. These metrics are designed to analyze various aspects of the interaction, such as cognitive load, attention utilization, and system redundancy, to enhance overall system performance and pilot experience. Evaluating the efficiency and effectiveness of feedback systems in aircraft piloting is crucial, with metrics such as feedback efficiency, FE, operational latency, OL, and critical risk index, CRI, providing valuable insights. A comprehensive framework is proposed to assess human and system performance under varying automation levels, incorporating metrics like cognitive load, human error, and system failures. The lumberjack model is utilized to monitor cognitive effects at high automation levels, accounting for different types of automation failures. This framework is applied to the SDT, evaluating quantitative metrics and providing a structured approach to enhance situational awareness and decision-making. In air traffic control, a systematic evaluation framework is developed to assess controllers' ability to detect and respond to signals amidst noise. Quantitative metrics, including hit rate, false alarm rate, correct rejection rate, and miss rate, are proposed to evaluate performance objectively. Qualitative metrics, such as operator stress level and decision confidence, provide a more comprehensive understanding of controllers' abilities. Scenario-based simulations that mimic real-world air traffic control situations are recommended, involving tasks that monitor radar screens to identify aircraft among noise, with stress testing and time-based assessments to evaluate decision-making speed. The use of datasets that closely mirror real-world air traffic control environments is emphasized, generating a wide range of possible conditions for thorough evaluation. Continuous analysis and refinement of the evaluation process are key, involving regular performance analysis, task modification, and operator feedback. Standardization and comparability are crucial, with standardized tasks and uniform metrics applied across all tests to ensure consistency. The development of this evaluation framework is supported by various studies on deep reinforcement learning, risk assessment, and human factors in decision-making, highlighting the interdisciplinary nature of this research. The research paper examines the implications of large language models for education, encompassing aspects from cognitive engineering, human factors, and artificial intelligence. It highlights the potential benefits in educational settings, including improved learning outcomes and enhanced decision support. However, it also emphasizes the need to consider the limitations and potential biases of these models, particularly in high-stakes decision-making contexts. The paper draws from key studies such as recognition-primed decision-making, the Oxford Handbook of Cognitive Engineering, and the capabilities of language models. It concludes by stressing the importance of understanding the limitations of these models and their potential impact on human decision-making processes.